Stir hot coffee and drop in an ice cube. Now tell me, with a straight face, how you'd make the reverse happen without cheating. I don't mean, could you in principle move some energy around? I mean the literal reverse. A lukewarm cup spontaneously separating into a hotter coffee region and a colder ice cube region, with the ice cube reforming, edges sharpening, the coffee getting hotter than it started, all by itself, while you watch. No freezer, no hidden pump, no trick where you quietly plug something into the wall. You've never seen that happen. You've seen the opposite 1,000 times. Ice melts in coffee. Warmth spreads. Things mix. Friction turns motion into warmth. The universe seems to have a preference. It takes organized, useful differences, hot versus cold, concentrated versus spread out, and smooths them away. And that is thermodynamics in its most honest form. Not 4 laws to memorize, not steam engines from the 1800s, but the blunt fact that some changes happen one way and practically never the other. Most people learn thermodynamics as 4 laws you memorize. Today we're going to pretend those laws don't exist and see if we can corner nature into revealing them anyway. Because the weird part is this: if you look down at the microscopic rules, the way atoms and molecules move and collide, the basic equations don't come with a built-in arrow that says forward or backward. If you filmed a bunch of idealized particles bouncing around and played the movie backward, the microscopic laws wouldn't scream. They'd look like perfectly legal motion. So why does your kitchen refuse to run in reverse? Why does perfume spread through a room but never unspread back into the bottle? Why does a hot pan cool down but a cool pan never heat up by stealing warmth from the air in a way you could harness? Why do you have to pay for a refrigerator with electricity instead of just letting it happen, the way cooling happens when you leave soup on the counter? If we can't answer that without chanting entropy increases, then we don't understand thermodynamics, we're just reciting it. So let's build the understanding from the ground up, no slogans, just things you can't argue with. Start with something almost insultingly simple. Take a box, put in a bunch of tiny balls, shake the box. At first, maybe the balls are all clumped on one side. After shaking, they spread out. If you keep shaking, you don't expect them to all clump back on the original side. Not because it's forbidden by mechanics, nothing stops it mechanically, but because it's ridiculously unlikely. Now replace the balls with molecules. Replace shaking with thermal motion. The box is your cup of coffee. That ridiculously unlikely is the first hint of the whole subject. But we should be careful. Unlikely can be a slippery word. A meteor hitting your house is unlikely too, and yet houses get hit. So what's special here? Why does unlikely become never for melted ice cubes and mixed coffee? Hold on to that question, because it's the thread that pulls the sweater apart. Before we talk about entropy, we need to get brutally clear about what heat even is. It's not a substance. It's a way energy moves when you refuse to track details. That sentence sounds odd on first hearing, so let's make it concrete. Imagine you have 2 objects, the coffee and the ice. You could describe them microscopically, list the position and velocity of every molecule. That's an insane diary. You can't do it. You don't do it. You never will. Instead, you summarize. You say, this region is at this temperature. That region is at that temperature. You say, the coffee contains this much internal energy. You say, the ice has this structure, these bonds locked in a crystal. Those are summaries. Now, when the coffee touches the ice, the molecules collide at the boundary. Energy is exchanged through countless microscopic bumps, jostles, and electromagnetic interactions. But you don't keep track of which molecule gave which molecule how much energy on Tuesday at 2:03 p.m. You just notice a macroscopic effect. The coffee cools, the ice warms and melts. When energy crosses that boundary due to a temperature difference, we label that transfer heat. Heat is not a thing inside the coffee. It's not a fluid sloshing from hot to cold. It's the name we give to energy transfer that occurs because of microscopic motion and collisions when we don't track the microscopic details. That's why we say heat flows, even though nothing like a substance is flowing. It's a bookkeeping label. And there's another kind of energy transfer that isn't called heat. If you stir the coffee, your spoon does mechanical work on the liquid. You're pushing and dragging. You're making the fluid move in organized motion. That's work. Again, not a mystical thing, just another label in the accounting system. Thermodynamics begins with a stubborn fact. If you include everything, coffee, ice, spoon, you're A. Arm, the air, energy is conserved. It doesn't vanish. It changes form. It moves around. That's not a thermodynamics law we're honoring because it's fashionable. It's a constraint you can't escape. Here's a simple example you can feel. Rub your hands together quickly. Your hands get warm. Where did that warmth come from? From the organized motion of your hands sliding past each other, turning into random microscopic motion in the skin and air. If you stop rubbing, you can't reverse it by having your warm hands spontaneously start moving in a coordinated way that lifts a small weight on the table. You don't see your hands cool down as they power a tiny motor. Yet if you're only thinking energy is conserved, both directions seem allowed. That's the pressure building again. Energy conservation alone doesn't explain the direction of what happens. So we're going to add the minimum extra idea needed to get direction, not by decree, but by necessity. Here's a strange question that unlocks temperature. If I add the same tiny bit of energy, why does it feel like a big deal in one system and a shrug in another? Think about a phone battery. When your phone is at 5%, adding a little charge feels dramatic. At 95%, that same little addition feels smaller in effect. Or think about a small cup of water versus a bathtub. Add 1 kettle of hot water to each. In the cup, the temperature jumps. In the tub, it barely notices. Temperature, in the most practical sense, is what you read on a thermometer. But a thermometer is doing something physical. It exchanges energy with what it touches until it reaches equilibrium, and its internal state, like the expansion of a fluid or the resistance of a metal, settles to a value. Temperature is the number that tells you which way energy will spontaneously transfer as heat when two systems touch. But that sounds like a definition that depends on the phenomenon we're trying to explain. So let's sharpen it. At the microscopic level, being hotter means that typically the molecules are moving around more energetically, more kinetic energy in translational, rotational, vibrational modes depending on the material. Still, that's not the full story because temperature is not exactly average energy. Different systems store energy in different ways. A solid has vibrations, a gas has translations, a molecule has rotations. You can add energy and it can hide in different internal pockets. So here's a cleaner approach. Temperature is the parameter that tells you how the number of accessible microscopic states grows as you give a system more energy. That's a mouthful. So let's put it in plain imagery. Imagine a huge building with rooms. Each room represents a possible microscopic arrangement of your system consistent with some macroscopic conditions. The system moves through these rooms over time as molecules collide and energies shuffle. If you inject a little energy into the system, you might unlock many new rooms that were previously inaccessible, extra ways for the system to arrange itself while still looking the same from above. In some systems, a small energy increase unlocks a gigantic number of additional rooms. In others, it unlocks relatively few. Temperature is a way of summarizing how expensive it is to move energy around and open new possibilities. High temperature typically means energy is cheap in the sense that the system already has plenty of accessible configurations. Adding a bit more doesn't radically change the multiplicity relative to what already exists. Low temperature often means energy is precious. Adding a bit can dramatically change what is accessible. Now, do you see what we just did? We smuggled in the key idea without naming it. The idea that the important thing is not the exact microdiary, but the count of how many microdiaries correspond to the same macro headline. That's entropy territory, but we're not going to jump there yet with a ceremonial unveiling. We're going to walk into it like it's the only door left. Consider your coffee and ice again. The coffee side has many microscopic ways to arrange its energy among the molecules. So does the ice. When they touch, energy can move from one to the other through collisions. Energy doesn't choose a direction because it reads a rule book. It moves in the direction that corresponds to overwhelmingly more microscopic possibilities for the combined system. That's the claim. Now we have to earn it. Entropy is not disorder. It's the number of microscopic stories that all look like the same macroscopic headline. Let's make microstory and headline precise enough that you could, in principle, count them. A macrostate is what you specify when you say, this gas has this pressure, this volume, and this temperature. Or, this coffee is at 60 degrees Celsius and is well mixed. Or, half the molecules are in the left half of the box. It's a coarse summary. A microstate is the detailed arrangement, positions and velocities and internal excitations of every molecule that would, if you zoomed out, appear as that macrostate. There are usually an absurd number of microstates corresponding to one macrostate. Now here's the move that changes everything. When a system evolves under microscopic laws, it moves from one microstate to another. But your macroscopic description doesn't follow microstates. It lumps huge bundles of microstates into a single label. So when you ask what happens next, at the macroscopic level, you're really asking, as the system wanders among microstates, which macro label will it land in most of the time? And that answer is dominated by counting. Let's do a tiny counting game you can hold in your head. Imagine 10 coins on a table, each coin either heads or tails. A microstate is the exact pattern, ETCHT, and so on. A macrostate might be how many heads are showing. How many microstates correspond to 5 heads? A lot. How many correspond to 10 heads? Only 1. If you shake the coins in a bag and dump them, do you expect 10 heads? No. Not because physics forbids it, but because there are far more microstates with 5 heads than with 10. That's counting, not mysticism. Now scale up from 10 coins to a number like 1023 molecules. Scale up from heads, tails to how energy is partitioned among all those molecules, motions, and posit. Ions. The number differences become so lopsided that likely turns into certain for all practical purposes. That's the backbone of thermodynamics. So let's return to the box of gas picture because it's the cleanest. Suppose you have a box divided by a partition, with all the gas initially on the left side. Remove the partition. The gas expands to fill the whole box. Why doesn't it ever spontaneously go back to the left? Microscopically, it could. The molecules could all happen to be on the left at some instant. But count the microstates. If the box is half left, half right, and molecules are randomly distributed, the number of microstates corresponding to half the molecules on the left, half on the right, is enormous compared to all on the left. In fact, the ratio becomes astronomical. You don't need the exact number, you need the shape of the argument. When you have a huge number of independent-ish choices, each molecule can be left or right, the most probable macrostate is the one with the greatest multiplicity. And with large numbers, multiplicity differences become overwhelming. That's why the gas spreads. Now, the coffee and ice aren't just molecules choosing left or right, but the same principle applies. The combined system has far more microstates, in which the energy is more evenly spread out, than microstates, in which energy is sharply segregated as hot coffee here, cold ice there. Melting increases the number of accessible microstates, more ways for the molecules to arrange themselves while matching the new macro conditions. Notice what we didn't do. We didn't say entropy wants disorder. We didn't give entropy a personality. We said there are more ways. So the next time someone says entropy is disorder, you can ask a pointed question. Disorder of what? Under what coarse description? Because disorder is a fuzzy human label. Counting is not. The second law isn't a banhammer. It's what you get when the universe is allowed to roll the dice with numbers so huge your intuition can't see them. But wait, if the second law is merely probability, shouldn't we sometimes see it violated? Shouldn't your coffee occasionally get hotter on its own? In tiny systems, you do see fluctuations. At microscopic scales, random motion can temporarily concentrate energy or particles in a way that looks like a small entropy decrease. That's real. It's not heresy. It's part of the statistical picture. So why is your cup of coffee so stubbornly one way? Because the probability of a large macroscopic reversal is not just small. It's small in a way that's qualitatively different from everyday small. Here's an everyday scale comparison that matters. Imagine you shuffle a deck of cards. The probability that the deck returns to the exact original order is tiny, but with enough shuffles, in an absurdly long time, it could happen. Now imagine the deck has not 52 cards, but 1023 cards, and you're not waiting for one particular order. You're waiting for the system to return to a highly special macro arrangement like all the energy bunched back into hot coffee. See, while the ice refreezes. The number of microscopic requirements for that is so large that the time you'd have to wait dwarfs the age of the universe. This is not poetic exaggeration. It's what exponential probabilities do when the exponent is enormous. So yes, the second law is statistical, but for macroscopic systems it is statistical with numbers so large that it behaves like a law of nature in practice. That's already a revelation. Thermodynamics is not a separate set of microscopic forces. It's what happens when you stop tracking details and ask what a system will almost certainly do. Now let's make the title's promise pay off. No one can teach you thermodynamics this way. The way is, instead of beginning with, here are the laws, we begin with, here is what you can predict without knowing everything. And then we find the rules that must be true for those predictions to be consistent. So what does this tell us about energy and usefulness? If you ever wondered why we can't build a perfect engine, the real answer is that energy doesn't disappear. It just becomes the kind you can't spend. This is where people get tangled, because they hear energy is conserved and think that means energy is always equally valuable. It isn't. A phone battery at 100% and a phone battery at 1% might contain similar total energy if you include the phone, the environment, the chemical bonds, everything. But in practice, one can power your screen and one can't. Value depends on constraints. Think about a waterfall. Water at the top of a cliff can do useful work. You can run a turbine. Water at the bottom cannot run that turbine. The total amount of water might be the same. The energy of the water might be conserved if you're counting properly. But the ability to extract organized work depends on a difference, height in that case. Heat engines are like that. A hot reservoir and a cold reservoir is a height difference in temperature. The engine is your turbine. The engine doesn't consume energy in the sense of annihilating it. It moves energy from hot to cold while extracting some organized work along the way. Now here's the question that should bother you. If energy is conserved, why can't we take a single reservoir, say the ocean at a uniform temperature, and extract work from it forever? If you could, you'd have perpetual motion of the second kind, a machine that turns random thermal motion into organized work without any other change. It sounds like free lunch. And the reason you can't is not that nature hates you. It's that the microstates are against you. To see it, try a classic loophole attempt. Imagine a tiny paddle wheel immersed in water, connected to a ratchet that only allows rotation one way. The water molecules jiggle the paddle wheel randomly because of thermal motion. If the ratchet blocks motion in one direction, maybe the random jiggling becomes a net one-way rotation, and maybe you can connect that to a little weight and lift it. Congratulations, you've made a machine that turns heat into work from a single temperature bath. This is the kind of idea people dream up because it feels like you're exploiting randomness. So where does it fail? It fails because the ratchet is not an abstract one-way gate. It is a physical object made of atoms sitting in the same thermal environment. Its pawl jiggles too. At the same temperature, the pawl will occasionally lift, the ratchet will slip backward, and the very thermal agitation you hope to harness will also undo the one-way constraint. The system reaches equilibrium, where there is no net lifting of the weight. That's not a moral lesson. That's the second law wearing a disguise. You can't get a net decrease in total entropy by sneaking in a one-way device, because the device itself is part of the system and must be treated statistically too. What's lovely about this is that it doesn't rely on because I said so. It's a consistency requirement. If the device is at the same temperature as the bath, then its microstates fluctuate as well, and any one-way bias you imagine is undone when you account for the complete set of possibilities. Now you might ask, fine, but I can build a motor that runs and does work. So what's different? The difference is that your motor consumes a low entropy resource, a chemical potential difference in a battery, a fuel-oxygen difference in an engine, a temperature difference between a flame and the environment. The motor takes a concentrated special arrangement and converts part of it into work while dumping the rest into the environment as waste heat, increasing total entropy. You always pay, not in energy necessarily, but in the quality of energy relative to the constraints. This is the bridge to the idea of free energy, the portion of energy that can be converted into useful work given a surrounding temperature and constraints. You don't need formulas to feel it. If everything is already at the same temperature, there's no height difference to run a turbine. If everything is already mixed, there's no concentration gradient to exploit. If everything is already at equilibrium, your ability to extract organized work is gone, even though energy is still there, swirling microscopically. So here's the catch. Thermodynamics is the study of what remains true when microscopic chaos is huge and your description is coarse. It tells you what kinds of differences are spendable, and it also tells you why the world has a direction. We can now return to the opening coffee and ice cube challenge and finally answer it with something more satisfying than entropy increases. If you want the reverse to happen, coffee heating up and ice forming, you need to reduce the total entropy of the coffee plus ice system. That means you need to shepherd the system into a vastly smaller set of microstates, a far more special arrangement than the one it naturally occupies after mixing and melting. Can you do that? Yes, but only by exporting entropy somewhere else. That's what a refrigerator does. It uses electrical work to force heat from cold to hot, increasing the entropy of the environment more than it decreases the entropy inside the fridge. It doesn't violate the second law. It pays the bill somewhere you're not staring at. Now you might wonder, if entropy is about count, in microstates, why do we talk about it as a physical quantity you can calculate, like joules per Kelvin? How does a count of ways become a number with units? That's a fair question, and it reveals something important. Entropy is tied to energy and temperature, because the count of accessible microstates depends on how energy is distributed, and temperature is the parameter that describes how that accessibility changes with energy. The units are there because we've scaled and connected the raw counting to macroscopic measurable quantities. The deep idea is counting. The engineering-friendly idea is a calculable state function. But we don't need to swim in units today to get the core understanding promised by the title. We need the aha that glues all of this together. So here's the punchline. Thermodynamics is what the universe forces you to say once you describe reality with summaries instead of microscopic diaries. That's the way no one taught you, and it changes what the subject even is. Thermodynamics isn't primarily a collection of facts about heat. It's a theory about prediction under ignorance. You refuse to track 1023 particles, so you compress your description. The moment you compress, many microscopic realities map to one macroscopic label. The system's true microscopic state wanders according to reversible laws, but your macroscopic label follows the bulk of probability mass, and that probability mass flows toward macrostates with overwhelmingly larger multiplicity. That's why equilibrium is so stable. It's not a special state in the microscopic world. It's the macro label that corresponds to the largest region of microscopic phase space given the constraints. That's why heat flows from hot to cold. Because for the combined system, the number of microstates consistent with more even energy distribution is vastly larger than the number consistent with energy staying bunched. That's why engines have limits. Extracting work means maintaining a special difference, and pushing energy through that difference while keeping your own device from becoming a loophole requires dumping entropy into a sink. And that's why time has an arrow in everyday life, even though the microscopic rules don't. Because the map from microstates to macrostates is many to one, and once information is lost into microscopic correlations, it's practically impossible to reconstruct it without paying an enormous price. Think of stirring milk into coffee. At the macroscopic level, you see white tendrils spiral and fade until you have a uniform tan color. Could the molecules rearrange themselves back into the dramatic spiral? Yes. Are the microscopic laws compatible with it? Yes. So why doesn't it happen? Because that spiral corresponds to an incredibly special set of microstates. The uniform tan corresponds to an astronomically larger set. As the system evolves, it wanders into the big region and stays there because there are so many more places to be. This is why thermodynamics feels like fate. It's not fate. It's combinatorics with ridiculous numbers. And once you see it like this, the subject becomes less about memorizing and more about asking sharper questions. When someone tells you this process is spontaneous, you can ask, what constraints are held fixed? What macro variables are we using? Where is entropy increasing? System, surroundings, or both? What resource is being spent? When someone tells you energy is conserved, you can reply, sure, but what about usefulness? What gradients exist? What differences can drive work? What differences are being erased? This is a different mental posture. It's investigative. It treats the second law not as a commandment, but as a consequence of the way we describe the world. Now let's end where we started, with that ice cube. If you want to see the reverse happen, you can. Put the coffee in a machine that does work on it. A refrigerator, a heat pump, a freezer. You'll see cold appear and ice form. But you'll also see the machine's back coils get warm, or you'll see your electricity meter spin, or you'll feel the air in the room heat up. Somewhere, entropy is increasing. Somewhere, microscopic possibilities are being multiplied more than you're reducing them in the coffee. That's the honest statement of the second law. Not bad things happen, but if you want a special arrangement, you must pay by making an even less special arrangement elsewhere. And there's something almost comforting about that. It means the universe isn't capricious. It is consistent. The next time something just happens, heat spreading, mixing, friction, you can ask a sharper question than why. How many ways could it have gone, and why did the numbers gang up on this outcome? Because once you ask it that way, you stop seeing thermodynamics as a list of facts and start seeing it as a lens that tells you why a broken glass doesn't unbreak, why smoke doesn't crawl back into the candle, why your phone warms up when it charges, why living systems have to keep exporting entropy to stay organized, why information has a physical footprint, and why equilibrium is not a mysterious attractor but simply the overwhelmingly common condition. And if you ever catch yourself tempted by a clever loophole, some device that seems to get something for nothing, don't immediately ask, what law does it violate? Ask, what did I quietly assume was fixed? What did I ignore that also fluctuates? Which microstates am I pretending don't exist? That habit is thermodynamics, not the vocabulary, not the formulas, the habit of never forgetting the counting.